Welcome to SanfordFlipMath. This is AP Calculus. We are steadily working our way through the Finney, Demana, Waits, Kennedy calc book. We are in section 5.3, and I know this top of the screen right now says 5.2a. We are going to make a quick connection and then move into 5.3. So just a reminder that this notation is really about area. We refer to it as an integral. And there's a lot of notation in here, and I'm not going to go over all of it, but basically this number right here is the left limit, or where we start the integral going left to right. This is where we end it. The b is. What we're doing the integral of is the integrand, or this function in here, and we're working with respect to a variable, so that's the dx. And the picture here is the idea that the dx is the width of, our little rectangle, and the height of our little rectangle is given by the function itself. So like if it was a left ram kind of situation, it would look something like that. So here's our dx, here's our f of x, the y value, and dx times f of x is that little area. That's the picture going on. Well, what we're going to look at in this next section in 5.3 is initially properties of integrals, and in the next video we'll talk about how that relates to what we've been doing through the first half of this course. So properties of integrals are just basically how we can play around with integrals, how we can work with integrals in a more mathematical or algebraic kind of way. So there are some things that we're going to focus in on just to kind of lay some ground rules, some ways that, some things that should make sense. Okay, so notice what's going on here in this first one. The order of integration has to do with how we are going left to right. Normally, we go from A to B. Notice this order has been switched. And so when that happens, it's like we're going backwards, and so there's a negative in there. So the book is basically saying, these are straight out of our book from page 285, if you want to refer back to them in section 5.3. Basically, whoever came up with this notation is saying, we're just going to say that that's what this means. Okay. So if we know the answer for an integral from going from left to right is 5, then if we're going from right to left, backwards, then we're going to say it's -5. That's it. Nothing real deep there. Okay. Second property is basically this idea that if I look at the area between A and A, okay, so these are the same, there's really not much area in there. Just a quick little example. Okay, so if I'm looking at the area from 3 to 3, okay, so I'm going from 3 to 3 of f of x. It doesn't matter what the function is. If that number's the same, there's really nothing there. Okay. Constant multiple basically says that if I multiply the height of this function, so if I had, this function here, and I multiply it by some number, like say if I double it, well, the effect on that is to double the area. Okay, so if I multiply the function by a number, the effect is to multiply the area by that number. Okay, so, remember, this is all based on rectangles. And rectangle, like this is base times height. So again, if I, maybe triple that height, if I do 3 times the height, the effect on base times height is going to be 3 times that answer. That's really what that's saying. Okay. And same is true for the specific idea that if k was a -1, okay, then it would be the same as if I multiplied the area by a negative. Now, we know that areas aren't negative. It just has to do with whether things are up or down. Okay. How we are going to use that when we're working with integrals is basically the idea that if I have a number multiplying a function that I know what to do with, I can kind of just ignore that number. I'm going to pull it out in front and handle the integral separately. So I'm going to handle this integral separately from that number and just multiply when I get done. Okay. Sum and difference, well, basically this rule just says if I want the integral of functions that are added together, I can actually do those integrals separately. Okay, so I can do those integrals separately. It looks on paper like distributing, It is not distributing. It's never distributing unless it's multiplication across addition or subtraction. But that's kind of how you picture it. So just like with derivatives, we can go through and do derivatives of each term separately. Well, we can do integrals of each term separately also. Okay. Now, this one is going to be a little tricky to see probably on the video, especially if you're on a phone. This was A. This is B. This is also B. And then this is C. So what this is saying is, if I'm looking at the area from A to B, and I'm looking at the area from B to C, this area, or I guess I need some kind of a function in here. Oh, now I'm changing colors. I'm just stalling. Just trying to make the video long for you. All right. So here's a quick. This is what it's saying. If I'm interested in taking this area from A to B, plus the area from B to C, well, if they share that point in the middle, then technically what's happening is I'm finding the area of the whole thing. Ooh, almost lost my marker there. So those two areas combined give you the whole thing. Okay, and that doesn't seem very deep, but remember what these properties are for is to kind of put in writing some of the rules that we're going to do. Okay, those are the biggest, the most important properties of the bunch here. Okay, 1 through 5 are the most important. I'm going to just talk briefly about 6 and 7. They're the most difficult to understand, and they're probably the least used, at least from what I've seen. Basically, this says if I have a minimum value of a function, a bottom to the function, so this would be the lowest height. If I do the lowest height times the base times the width, if I take the maximum height, okay, that's on the other end, the maximum of the function times the width. So this gives me the maximum height times the width is the biggest area. The lowest height, the minimum height times the width gives me the lowest area. And basically the idea is the true area between a function, between a curve and the x-axis has to be between those two. Okay, so just to do a little picture of what's going on here. Okay, so this is to try and illustrate property number 6. Okay, I have some lovely function, and I'm talking about in between A and B. And if I go to the lowest height on A and B, I don't know, let's just pretend it's here. I probably should have made it a little more obvious. If I go to the lowest height between A and B, this is going to be, and if I find an area, okay, so the lowest height times A minus B, here's my width. If I then go to the highest area between A and B, or the highest height between A and B, and I find that area, the true area for this thing, which should be this area, the true area has to be between them. Maybe I don't know what that area is, but the idea, this is kind of analogous to the Sandwich Theorem before, when we said a limit had to be between two numbers, and if you got those numbers to be the same, then you knew what the limit was. You know, usually it was a trig function kind of thing. Well, similar idea here, only we may not squish it down to an actual number for the area. Okay. All right. Well, I'm not going to spend my life on that. Okay. And then the last property on this, number 7, is kind of similar. And again, I don't see it as used as often. If I have a function that is always bigger than another function, then the integral should be bigger than the other integral. I think that's kind of intuitive. If we're talking on the same width, the same a to b, if all these y values are bigger than those y values, then the area is going to be more than that one. Same idea here. If one of the functions is just y equals 0, if this function is always positive, then the area has to be positive. That's really it for that. All right. So with that in mind, with those in mind, let's take a peek at how some of this gets used. Okay. All right. These are examples stolen straight out of your book, page 286. If you're looking for more of what this is in writing, you can go there. So here's the idea. Let's say I already know some information about some integrals, f, and, for functions f and h, and I just know some specific information. I don't know what the original equations are. I don't care. I just know that the integral from -1 to 1 for f of x is 5. The integral from 1 to 4 of f of x is -2, and the integral for h of x from -1 to 1 is 7. That's given information. I know that. So a through f now are problems based on that. What we're supposed to do then is we're supposed to figure out what the integral from 4 to 1 is for f of x based on the other information we see. So what you want to do is apply those formulas. Now, you have to kind of browse around and see where these came from. Like, for instance, this 4 and this 1 for f of x. Well, here's f of x. That's not 4 and 1. Here's f of x. It's 4 and 1, but they're switched. Okay, well, we had a cute little property back here that said that if the order is switched, then the sign changes. Okay, so for a, it has to be whatever the negative of -2 is. So let me just kind of clean this up. I'm not going to write it down there. Okay. So this one is just going to be the opposite of -2, or in other words, 2. That's it. Okay. Okay, let's take a peek at B. B says from -1 to 4. Well, this is not -1. That's -1. So the idea here is if I go from -1 to 1, that integral is 5. When I go from 1 to 4, that integral is -2. This 1 is kind of bridging the gap here. So this is number 5. That gets used a fair amount. So here's 1 to 4 and 4 to 5, or no, I'm sorry, it was -1 to 1 and then 1 to 4. That's what it was. -1 to 1 and then 1 to 4. So this becomes, not plus, sorry, equals 5 plus -2, also known as 3. This is from -1 to 1. Well, here's -1 to 1, and here's -1 to 1. Here's f, here's h. I'm going to do a number of things here because there are a number of things going on here. But it's all going to be about this guy and this guy. Okay? So I'm going to break this up. Now, some of you are going to see right away what to do with this, and you're just going to say 2 times 5 plus 3 times 7 and add that up. I'm going to be a little more picky about the algebra or the substitutions right now because I'm trying to make sure that the properties are clear. I have addition, excuse me, for two different functions being added together inside the same integral. I have a property that says I can break that up. So I'm going to write from -1 to 1 of 2 times f of x dx plus from -1 to 1 3 times h of x dx. You must have the dx's on the end. That's proper notation. Don't leave them off. Now I have a property that says if I have a number multiplying, I can bring it out. If I have a number multiplying, I can bring it out. So I'm going to do that. So 2 times the integral from -1 to 1 f of x dx plus 3 times the integral from -1 to 1 h of x dx. Okay, now I'm going to do some straight substitutions. For instance, I know that f of x from -1 to 1 is 5. So this whole thing right here is 5. So 2 times 5 plus 3 times, well, from -1 to 1 for h is 7. So this whole thing is 7. So 10 plus 21 is 31. Okay, so that's the answer for C. Okay, so the answer to your next question is no. Do I need to see all that written out? No, I don't. Do I need you to understand how it works? Yes. If it helps you to write it all out, write it. Okay, I'm not going to be nitpicky about every little step of substituting and every little property there, but you do need to know how it works. Okay. All right, f of x from 0 to 1. Okay, so I don't see a 0 as a limit to integrating in any of these. Okay, I don't see 0. Like for instance, I see that says f of x from 0 to 1. This says f of x from -1 to 1. If I knew this was an even function, if I knew this function was symmetric over the x-axis, or the y-axis, excuse me, on the left and right side, then maybe I would know we could just cut this in half. I don't know that. I don't see an x value of 0 anywhere for f of x at all. So honestly, I really can't do anything with this. So I know this seems weird, but there's not enough information here. Just can't do it. Can't do it. Wouldn't be prudent. Okay, that's it. Okay. I mean, I don't know, for all I know, I know that the area from -1 to 1 is 5, and for all I know, the thing looks like this for f of x, and if that's true, I don't really know the steepness of the line. It could be a curve. There are a million things it could be. I just don't know. Okay. All right, well, let's look at h of x from -2 to 2. Well, again, I don't know what h of x looks like. If I knew that h of x was, like a constant function or something like that, if I go up instead of from -1 to 1, I know that area is 7. If I knew more about it, then doubling the length on each side maybe would double the area, maybe. But I don't really know. So I don't know enough information to do that one either. I mean, as annoying as that is. Okay. And then last one here, I can break this up and say, so this is for f, okay, and I know things are getting a little tight here. From -1 to 4 f of x dx plus -1 to 4 h of x dx. Okay, so -1 to 4, that's -2 for f of x plus, I don't know what to do with h of x. Can't do it. Okay, sorry, just wouldn't be prudent. Can't do it. Not enough information. Okay. All right, we have one more idea to do, and unfortunately this idea takes a little bit of time, and we need to explain what it means. Ha 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 ha. Pardon the pun, but it's not an obvious thing. Okay, so what we're trying to find is the average value for a function. Now, we have a conceptual idea of what average means. Like if I have 2, 3, 3, 7, 10, and I wanted to find an average, I would add them up and then divide by the number of items I had. So in this case, I would add them up, and that's 25 over 5 numbers. The average is 5. Okay. Well, how do you add up numbers when you're talking about something that looks like this? Let's say, here's A, here's B. I want to know the average value of y from A to B. Well, how many y values do you see there? I mean, the problem is that even though I have a definite starting point and a definite stopping point, for, a bottom y value and a top y value, and I'm going to guess that the average has to be somewhere in between there. There are really an infinite number of y values here. Like if this was at, let's say, y equals 3, and let's say this was, y equals 7, the average y value could be anything between there. And I have, numbers like 3 and 3.1 and 3.127, and every number between 3 and 7 is in there. There are an infinite number of values there. And how am I going to add all those up and then divide by infinity? I mean, you just can't do that. So what we end up doing is we do what is as close to we can as a sum, and that's an integral. This is, remember, the idea is this is an infinite sum. It's a limit. Okay, so, and then we can't really divide by the number of values. What we do is we divide by the width, or the b minus a. Now, technically what is happening is we're finding an area and we're dividing by a width, or a base. And when we do that, if you think of it in terms of like a rectangle, what we find is a height. So what the average of a function is analogous to is the height that would produce a rectangle with the same area. A height that produces, that makes, I should have said makes, a rectangle with the same area. Okay, now let me just kind of give you a heads up. I kind of think this is a big deal, so you're going to have to wrap your head around this. If I find the area underneath this curve from A to B, and it has an area, it's going to have an area that's equal to base times height, or in this case, sorry, not A, B minus A, that's my base, times my height, and I'm telling you the average, the height is the average value of f. Okay, so the area from that integral is equal to the width of that region times the average f. So if I divide both sides by the width of that region, that's where this comes from. Okay, sorry about all the scrolling. Okay. All right, hit pause, stare at it for a minute, and understand what it's saying. One more thing to go with this idea, and that is the idea that this is called the mean value theorem. You've seen that before, of definite integrals. Mean value theorem before said there is some spot where the derivative equals the average rate of change. Or we talked about it as the slope of the tangent line is equal to the slope of the secant line. What this says is there is a spot, x equals c, there is a spot where, wasn't that magical? All right, there is a spot where that area of the under the curve, the integral, the area under the curve, is equal to the area of a rectangle. There is a spot where that average height actually crosses the function. There is a spot where the y value for this function is the average, and the c value is that x value. Okay, I'm not going to do any examples with this. We'll play with it in class. I just wanted to introduce the topic here, and this is already pushing it. You know how I like to have my 20-minute videos. Yeah, right. Okay. So here's a conceptual idea of what's going on. We will play more with this in class. Thank you very much. Bye.